Okay, just using some of these properties that we just learned. If k equal 1 to n of a sub k equals 7, and if the summation from k equal 1 to n of b sub k equals -4, find the following values. And so not skipping any steps whatsoever. First of all, I can break up summations by subtraction. Then I can then factor out those coefficients. So I have 7 times the summation from k equal 1 to n of a sub k minus 1/30 the summation from k equal 1 to n of b sub k. Then they gave me each one of those values. They told me that the summation from k equal 1 to n of a sub k was 7. And they told me that the summation from k equal 1 to n of b sub k was -4. And so I have 49 plus, divided by 2, 2/15. And I'll go ahead and do that. That's not so hard. That is 735/15 plus 2/15 for 737/15. Again, the arithmetic, not the point. Don't worry about the arithmetic. So once you get down to here, take out a calculator, do your arithmetic. The point is just doing a little bit of work with those summations. Now it's a summation formula. So now these previous rules, you really should be aware of these previous rules and be able to use them. So you should know these and be able to use them. These following formulas you do not need to memorize. If they appear on a test, or if you're watching these videos sometime in the distant future where things are back to normal and I'm giving quizzes, you don't need to memorize these. If they appear on a test or quiz, I will give you these formulas. I'm not going to make you memorize for, as old as I am. I have still yet to successfully memorize the second one. I look it up every single time. But here are some formulas for certain summations. K equal 1 to n of k, so 1 plus 2 plus 3 all the way up to n, is always given by n times the quantity n plus 1, the whole thing divided by 2. The summation from k equal 1 to n of k squared, so 1 plus 4 plus 9, so on, is given by n times the quantity n plus 1 times the quantity 2n plus 1, whole thing divided by 6. And lastly, k equal 1 to n of k cubed, so 1 plus 8 plus 27 all the way up to n cubed, is n times the quantity n plus 1, all divided by 2, the whole thing squared. So there's some formulas for k, k squared, k cubed. You do not need to memorize them. Let's use them a little bit. So doing this first guy, and again, not skipping any steps. So first of all, I can break up that addition into two separate summations. The summation of a sum is the sum of the summations. And now I can use my formulas. In this case with n equal 4. So I'm using this formula up here with n equal 4. We'll actually write that down in red here. Use n plus 1 over 2 with n equal 4. And over here we're going to use n plus 1 over 2 squared with n equal 4. And so this is going to become 4 plus 1 over 2 plus 4 plus 1 over 2 to the 5th. And now it's just arithmetic. The 4 and the 2 are going to cancel there, so I'm going to get 2 times 5 plus 2 times 5 squared. Which gives me 10 plus 100 for 110, assuming I didn't make any mistakes in my arithmetic. And again, the computation's on the end here, not the point. The point here, understanding I could break it up, and then understanding I had formulas there. Same thing on the next guy. First, I can break that up, and I can factor out that coefficient. So that's going to be 3 times k equal 1 to 5 of k squared minus k equal 1 to 5 of 6. Then my formulas. Use, and like I said, I can never memorize this one, so I'm looking over on the piece of paper, n, 2n plus 1 all over 6 with n equal 5, and here use Cn with n equal 5 and C equal 6. Make that a little bit neater. So this becomes 3 times 5, 5 plus 1, 2 times 5 plus 1, all over 6, minus 6 times 5. And then it's arithmetic time. Again, point not the arithmetic. But notice here, 5 plus 1, that'd be 6. 6 in the denominator. Those divide. So then I have 3 times 5, which is 15. 3 times 5, 15. And that's going to be 11 minus 30. And then we'll ask the calculator for the rest of that. And that works out to be 135, assuming I did not do any of my arithmetic wrong, and the point is not the arithmetic. Again, the point is realizing you can split it up that way, and then realizing you had formulas. Okay, so now it's time to put together what we did in the last section about estimating areas using just a few rectangles and our summation work to make it become finding exact areas. So, finding exact areas. Previously, we estimated the area under our graph of f of x equals 16 minus x squared between x equal 1 and 3. Previously, we estimated that. In the previous, we used 4 approximating rectangles and calculated the area would be between 21.25 and 25.25 square units. We now want to find the exact area. To do this, we will still use rectangles, but we will consider using infinitely many rectangles. Okay, let's go. Now again, this is kind of foundational work, getting us to a very, very, very important theorem. This is kind of the hard way of doing things before we get to the easy way. So if this blows your mind, don't worry too much. It's not the major point of the class. But it is important. It's foundational stuff. And it's important that you understand the foundation, but you don't necessarily have to build the foundation. Okay. The instructions, here it says My Math Lab. I think they've changed that to My Lab Math. I should open up my notes or update my notes. But the instructions you're likely to see in the computer. Assuming that they are still the same instructions. It's been a while since I've really read the exact instructions there. But you're likely to see something like this. For the function given below, find a formula for the Riemann sum obtained by dividing the interval into the given interval into n subintervals and using right-hand endpoints for each c sub k. Then take the limit as n goes to infinity to calculate the area under the curve on the given interval. And this is so bizarre, and I took I follow the textbook, Your textbook actually talks about Riemann sums more in the next section. But just a quick foreshadowing of what a Riemann sum is. A Riemann sum is that idea of adding up areas of rectangles. And if you were standing in, if this was a classroom in front of me, I would have put air quotes around areas. Because if my rectangles are below the x-axis, the value I get by height times width, since it's below the x-axis, would be negative, and I shouldn't call negative numbers area. I have seen several YouTube videos where they talk about negative area, and that just rubs me the wrong way. So I'm always just going to put area in air quotes with the understanding that if my rectangle is below the x-axis, not in this application, but in some other applications, if your rectangle is below the x-axis, the resulting area, in air quotes, will be negative. But all a Riemann sum is, and I kind of digress there, Riemann sum is just that concept of adding up areas of rectangles. That's all it really is. Okay, so what the instructions mean. These instructions mean find the exact area on the function on the given interval using infinitely many rectangles with right-hand endpoints. Now, all we mean by right-hand endpoints is that the function, the rectangles are going to meet, the curve will meet each rectangle on the right side of the rectangle. That's all we mean by right-hand endpoints, that the curve and the rectangle are going to meet on the right side of the rectangle. So, we have the same region that we did before. Consider the region bound by f of x equals 16 minus x squared and the x-axis on the interval from 1 to 3. Find the exact area. So, what I would do, same thing I did before, I start drawing in my rectangles. And I'm using equal width rectangles, so to the best of my ability on my computer, I drew in several representative rectangles. S1, S2, S3, dot, 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 to represent rectangles I didn't draw. Then a representative rectangle, S sub k, and then my final rectangle, S sub n. Each one of those rectangles gives me an x-coordinate down below. So S1, the right-hand endpoint, or the right-hand endpoint would be at x1, then x2, then x3, then x sub k, x sub n. So those are all just the x-coordinates defined by each rectangle. And then just like before, that height right there, I'm going to get by taking my x-coordinate, x sub k, and plugging into my function f of x sub k. So it is very similar to what we did before, and I still have those notes here. Very similar to what we did before, but instead of having 4 rectangles, I have now drawn in representative of many, many, many rectangles. So I did what it says down there. First, draw several representative rectangles, label the rectangles S1, S2, so on. The exact area can be obtained by adding the areas of all the individual rectangles as we consider infinitely many rectangles, or that is, as n goes to infinity. That I drew in here n rectangles, we're going to consider infinitely many rectangles as n goes to infinity. This could be expressed as the area equals, the limit as n goes to infinity, of area of S1 plus area of S2 plus area of S3, dot, 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 area of S sub k plus dot, 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 area of S sub n. That I can find that exact area if I fill it up with infinitely many rectangles. Because what's happening when I put in infinitely many rectangles, these rectangles keep getting smaller or narrower and narrower and narrower until each one of those rectangles becomes just a line segment. And then what you're doing is you're adding up infinitely many line segments. Now here's what's cool, and I'll try to say it in the last 30 seconds of this video. I'm adding up infinitely many line segments. Line segments are one-dimensional. They only have length. I'm adding up infinitely many one-dimensional things, and that will become two-dimensional area. That's cool. Add up infinitely many one-dimensional things, and you get a two-dimensional thing. End of this video, and we'll pick up right here on the next video.